So good morning, Kevin.
Good morning, Harry.
So today we are going to talk about this absolutely fascinating story, which goes back more than 5 decades, of the Apollo missions after the moon landings. You know, they brought back some rocks back to the Earth, and those rocks were later found to contain iron crystals, beautiful iron crystals. Okay. So tell me how these iron crystals feature in the study that we have published.
Well, these iron crystals are interesting iron crystals in the sense that they are very small iron crystals that you can only see by using techniques such as scanning electron microscopy. They are of the order of 1 micron in size, so they're far less large than the width of a human hair, to give you some feeling of dimensions. And so you have to use something like a scanning electron microscope. Fortunately, even in the early 1970s, there was chemical analysis facilities available in these microscopes, and they were able to establish beyond reasonable doubt that they were essentially pure iron crystals. You could argue there's a 0.5% nickel, but essentially as an impurity, but it's essentially pure crystal.
Yeah, I mean, didn't they say that the nickel figure was below the limit of detectability or something?
They were covering their backs very nicely, as scientists should do, by saying that it was below the limit of detectability, which of course is a way of saying we can't exclude the possibility of nickel, but we think it's below this reasonably low limit. So, and that's completely different from the iron meteorites that one hears about, where the iron meteorites are, it is correct in the sense that they contain iron, but they also contain rather large quantities of nickel. And so you get these what are called Wittgenstein patterns in these iron precipitates, but they're completely different in composition because they've got a lot of nickel.
And the scale is very different.
And the scale could be on the order of meters, for example, in extreme circumstances. In examples you find in museums, they are on the scale of even 10 centimetres or so would be not unreasonable.
Yeah. I mean, at the Smithsonian, I've seen a meteorite more than a meter big.
Well, that's quite impressive. Yes. But so these are, as we've stressed, 1 micron in size. So that's of the order of the wavelength of light. So that's why you have to use scanning electron microscopy to be absolutely certain that you see these things. And when you do see these things in the scanning electron microscope, they have these very specific morphologies. So
but first of all, Kevin, explain where with respect to the rocks that were brought back, were the iron crystals found?
So in mineralogy, the terminology is that they are crystals found in vugs, which are part of lunar breccias. So in layman's terms, which you and I understand better, well, it turns out that breccia is the Italian for rubble, and so rubble is essentially a conglomeration of bits of different minerals glued together by some concrete-like species which helps to bind all the crystals together in this rubble. And within this rubble, it's not absolutely 100% dense, so there are holes. They call them vugs. We could call them cavities, but let's call them vugs because it's something which means that mineralogists can differentiate themselves from other people by saying we know what that terminology is. Very useful for Scrabble, but once you work it out, it's basically small crystals found in holes or cavities in rubble or lunar rubble, which of course is very precious lunar rubble because it's being transported back to the Earth from the Moon.
And how exactly do these crystals form inside these vugs?
Well, they form from essentially a vapour, and which will be containing iron, but containing other chemical elements such as silica, such as oxygen, and it just so happens that the later stages of cooling, so you get the breccias, which are
when the other crystals are formed.
They formed as well, and these iron crystals are the last crystals to form, and they are excitingly interesting because, okay, so the crystal structure of these iron crystals is what's called body-centered cubic iron. So these are where the iron crystals packed together in a regular arrangement defined as body centre cubic. The atomium in Brussels, for example, has a large
Cube.
sculpture of b.c.c iron.
Mm.
Now, and so you might think that simplistically, you know the crystal structure is cubic, then they might form cubes. But in this case, they don't form cubes. You might also think they form other crystal shapes where the external planes defining these crystals have got what are called low index Miller indices to do, and this comes back to the crystallography of these little crystals. But these are unusual in the sense that you've got some of the faces are what I would call Q planes, and other of the are planes which in Miller indices are HHL, and this is different from what you see in very, very small pure iron crystals found or produced synthetically on the planet Earth.
Yeah. And the crystals, you know, the reason why crystals often have facets is because they're trying to minimize the overall surface energy.
It's a surface energy problem, yes.
So, do these moon crystals actually correspond to an equilibrium shape?
They correspond to a very non-equilibrium shape in the sense that the shapes are have a combination of what are called in Miller indices 100 type facets, and these other facets which are of the general form HHL. The geologist at the time working in the early 1970s in NASA just described them as HHL facets, and I suspect that they were just happy with that because it was a different morphology from what other people had seen on the planet Earth, and they said, look, we found something different, and they didn't feel the need to, as it were, go deeper and try to ascertain what the possible indices of H and L might be.
And that hasn't happened for the last 50 odd years, right?
And by doing a careful literature search, A, before we wrote the paper, and B, informed by the referee's comments for the first draft, fair enough, we did a further check to find out that actually the original NASA papers had not been that well cited, and clearly where they had been cited, people weren't just in the least bit interested in what H and L might be, the specific facets. From the point of view of somebody who knows a bit about crystallography, you could look at the crystals, look at the scanning electron microscope images, and they didn't look as though they would be, say, 112 facets. They just didn't correspond to what you might have when you look at mineralogy or crystallography textbooks, such as F.C. Phillips' book on Introduction to Crystallography, which I myself had as an undergraduate when I was at Cambridge.
Yeah, because they tend to have planes with a high packing density of
they'll have planes, so in what are called in Miller indices, the terminology 100 or 110 or 111, possibly 112, but exotic indices, like the ones we actually feel that are there in these moon crystals, well, these will form because, of course, the crystals, there's an energy minimization argument, but it's to do with the fact that the atmosphere within which these crystals form is some sort of soup of unknown composition to us, and it'll be minimum given that atmosphere within which the crystals form.
And
so
the sort of, if these crystals formed on Earth, they would very rapidly be destroyed by moisture and so on.
That is very likely.
So these are actually found in pristine condition, aren't they?
We can assume there's very little moisture on the moon. This is one of these things where there's a lot of speculation about whether there's any moisture on the moon or Mars or any other planet of your that you might like to think about. But the reality is most of the moon is going to be very, very, very low moisture.
And inside the bog as well, these cavities might have been closed.
They may have been protected from any unintentional vapour around, yes.
So basically these crystals look absolutely beautiful.
They look very beautiful, and they are reasonably symmetrical. Some of the crystals, we analysed 5 crystals, but I think it was 2 of them looked reasonably symmetric. That is to say, they had the external symmetry consistent with that symmetry of a cube. That you can, with which people are familiar.
Which people call M by 3M.
which people call M bar 3M, where it's got four-fold axes of symmetry called tetrads, three-fold axes of symmetry called triads, and two-fold axes of symmetry called dyads. Yes, to use the technical nomenclature. Yes.
Yeah. So, how do you go about discovering what these HHL indices actually are, given the limited information that we have in terms of, micrographs published by NASA?
So what we were having to look at were the 5 freely available micrographs published by NASA. When I say freely available, well, one of them is easily available, there's a web link to that. 2 others are in literature or in journal papers, and we had to take very high resolution scans of those images to persuade ourselves that that was the best quality in which we could use the analysis. So, but the problem is, you know that the faces that you're trying to index are going to be of the form HHL, and you might think, well, okay, let's assume, and we know that L has got to be greater than H, that's another limited boundary condition. The conditions under which the micrographs, the scanning electron micrographs are taken, it's a reasonable assumption, because of the magnification used in because they're 1 micron in size, it is a reasonable assumption that it is what's called parallel projection illumination.
Yeah, because we are working with 2-dimensional images.
Because essentially what you're looking at is a 2-dimensional image from a 3-dimensional object. So, and you have to try to use essentially projectional geometry, and it is relevant whether the parallel projection assumption is a useful and relevant, because that makes the geometry far more easy.
That's right, because if it wasn't a parallel projection, it would be like a perspective, so distant objects would be further away, and effectively you are distorting the...
So, and people in material science are hopefully nowadays reasonably still happy with the concept of stereographic projections, which is where the central projection is nothing like infinity at all. So it's the south pole of a sphere, for example. So in
a sense, we are lucky that we can approximate this.
So essentially, this was a very defensible and reasonable approximation, and it's the approximation you really want to use unless there was a compelling argument not to use it, and it turned out there wasn't a compelling argument not to use it, so let's go for it. Yes. Yeah. So that was the first part of the puzzle. The second part of the puzzle is that, well, these crystals are 5-sided, which actually you think, oh, 5-sided.
The faces are...
the faces of the crystals, the ones which are not obviously 001 type or 100, they've got 5 sides to them. Now you can dismiss straight away anything to do with icosahedral symmetry. The 5 sides reflect the fact that you've got you have 100 type facets and HHL facets. That's fairly straightforward.
Because you could actually make the whole crystal with just the HHL
You could make something
facets.
which is something icosahedral, yes.
Yeah, and you would have 24 faces, each face shaped like a kite with 2 sets of sides of
you could,
different lengths.
And they'd be yes, you could, but if be of the form 1 tor 0, which is not the same thing.
Right.
Where tor is square root of root 5 plus 1 all over 2, 1.618034.
Yeah, and that the 24-sided object is what you call deltoidal icositetrahedron.
This particular, when it's the HHL faceting, it's the deltoidal icositetrahedron, and that's the terminology used by Phillips.
And the 001 planes basically truncate that.
And the 001.
And that's why we get the 5 sides, which is
which is
the puzzle that inspired the study.
So that's how you get the 5 sides. You then realise that every HHL face has got nearest neighbours, which obviously, and 2 faces meet in a line. So that then determines the vector directions of those 5 lines, the parallel or anti-parallel vectors, and you can make it quite general that if the face is of an index HHL and one of its surrounding, one of the adjacent faces is, let's say, bar HL, you can work out what is the line common to those two faces, and you can do that systematically, so to define the vectors which define those 5 lines, and then you have to say, well, okay, so imagine that this parallel projection is along the direction UVW, and then we can work out what the vectors, well, what those 5 vectors would appear to be like
looking
projection down that UVW direction. So we can then use that to work out the angles seen in projection between the 5 vectors defining the face of that crystal. And we can do that for actually not just one of those faces, but all of the 24 HHL. And it is not enough to just look at one face and hope that your measurements are so spectacularly accurate that in and of itself will define the indices of the HHL, and that you can defend your choice of UVW. It turns out that for 2 of the crystals where the external symmetry really was the same as the m bar 3m symmetry for a cube, actually you can use from the projectional geometry, you can work out a very good idea of what the UVW direction must be, because of the symmetry of what any crystal will look like when seen along a general direction UVW. There's a little bit of mathematics which works out where that direction would have to be on that projected image of that crystal, and that's quite useful as a check. But basically, what I ended up doing was doing lots of Excel spreadsheets over the Christmas just after the Christmas period of December 2022, and my partner at home was thinking, well, what's he doing all this for? So it's essentially, you can look at this as being like a Sudoku puzzle. You like to solve a Sudoku puzzle. And so I actually then developed a program so that you could, for any 8 values of reasonable values you might want to look at for H and L, you could see what the crystal would look like under a particular projection choice UVW, and compare it with what you see on the image.
And of course, you're not just comparing how it looks, but also the angles measured on the micrographs and so on.
You're looking at all the information available, well, essentially all the information available in the scan electron microscope image. So what faces are almost parallel to the electron beam, what are slightly off being parallel to the electron beam, in addition to the ones which are clearly not parallel to the electron beam and are looking at you, as it were, as you look at them. And it's not, so it's the totality of the information. So so that is why when it came to the analysis, and we were also making the reasonable assumption that all of these crystals found close to one another, surely they'd all have the same value of H of L because of the environment in which they had crystallized. So that's again a reasonable assumption. They look similar, so perhaps they are similar. So when it came to analysis, we tested various faces. The possibilities like 116, but it clearly wasn't 116. 115, 114, they looked pretty good, and there were some subtle differences between the two. Sometimes one looked better, sometimes the other looked better. But if you took 229, that was quite a sort of reasonable compromise and defensible compromise. At the other extreme, something like 223 or 112, clearly not. It was entirely inconsistent with that. But 115, 114, 229 is a sensible compromise. So you could argue that we're hedging our bets by saying it's 229. But the subtleties between 115 and 114, you could argue that, well, perhaps that's going back to this parallel projection assumption wasn't quite as good as it could have been. And if somebody wants to come along and look at our data and say, well, actually, let's tweak that parallel projection approximation and come up with either 114 or 115 as the definitive answer, well, at least we'll have led them pretty much along the right path to the correct solution. So, and by also analysing crystals which weren't perfect,
which had different sizes of all one
crystal had one particularly large facet, 001 facet, for example. we could actually again reproduce what the images would look like in the absence. One or two crystals had clearly other crystals attached to them as well, or blobs.
Right, blobs. They look like blobs. Yeah.
They look like blobs. And then one crystal was elongated in along one particular direction. And again, with a bit of vector algebra, straightforward vector algebra, you can analyse this and again come up with projectional geometry images of what these crystals would look like, assuming the facets was particular things and assuming that the projection direction was again one which you could defend as being reasonable. And you use the same projection direction that was your best estimate for all those different geometries.
So I should add that all this analysis, including the algorithms, are actually available on the web.
Yes, I sent those to you by email, and you put them on the web. And if people like ploughing through Excel,
because they're actually quite interesting.
And you can play with things, play with the data as well. Yes, so it's all out there.
So, Kevin, let's assume that the analysis is absolutely correct, 2 to 9. Why would nature choose to have such a crazy set of indices?
Well, it comes back to the unknown impurities in the atmosphere surrounding the iron crystals when they were growing. It's as simple as that. It turns out that mineralogists are very happy to basically say, well, it's to do with the impurities surrounding.
But there are other studies on other crystals where impurities have been shown to result in high index planes.
Yes.
Is there any other reason why this might be a high index plane?
Well, with high index planes, the nice thing about high index planes is they can replicate themselves quite easily because they are going to be composed of, let us say, steps and ledges. And because you've got these defects between the steps, at the step-ledge interfaces, that can help to propagate the same low or high index plane.
Makes it easier for atoms to deposit.
And it makes it easier for atoms to deposit, but ultimately you'd have thought that the step would be the dominant plane which would form, and in this case, if it's of the form HHL, you might naively assume that 112 might be a low energy facet, but actually we see that so you could have 112 type facets and 001 type facets, or 001 steps, causing these macroscopic 114, 115 planes.
It's common in growth theory.
It is certainly common as part of the growth process, but usually you find that ultimately at the end of the growth process, the external morphology is dominated by adjust, so the low energy planes are produced. But as I say, in geology, the very fact that they find all these different forms of the same crystal, they're quite happy with it.
So, Kevin,
a second example would be iron pyrites, for example. That anybody who's ever been to a mineral shop or visited caves, you find there are lots of them are cubic, and they're 10001 type facets. But there are also the more interesting varieties of iron pyrites crystals which you can purchase, which are 210 facets, which are icosahedral-like.
Excellent. so Kevin, just to finish off, you know that NASA is planning more missions to the moon and even to establish a moon base.
Yes.
Wouldn't it be exciting if you could ask them to bring us some pristine iron crystals so that we can subject them to, modern analysis techniques and close the problem?
It would be, yes, and gosh, it's over 50 years since man, and of course it was an American. There are 12 Americans who have set foot on the moon. Very popular pub quiz question. But there are only 12 American men who've stepped on the moon. It'd be nice if we could have technology which allowed that again, yes.
Yeah.
And again, it's one of these things where it ultimately comes down to money. Yes.
Well, they are, they are going to establish a moon base, so it would be easy to go and pick up some of these rocks, I assume. Okay.
I assume so. And of course, it'd be nice equally to do this on other planets such as Mars, but there again, getting to Mars and having somebody land or step foot on Mars, that's a challenge.
But funnily enough, the Mars lander has collected samples and left them there for the next lander to come and pick
yes,
up.
because they can't bring it back. Yeah, yeah.
So
and I don't
we'll
know
see.
what's happened with their analysis at all, but that's actually good that something has landed on Mars rather than crashed into it, and actually we can get samples.
Thank you very, very much.
Thank you. Right.